our July Lectures in Physics for 2016, celebrating the 100th anniversary of Einstein's theory of general relativity. Appreciate everyone coming here on this cold, bleak Melbourne night, and any of you who were here on the previous lectures for making this program such a success. We still have a few people looking for a seat, so if you wouldn't mind, if there's a seat to the left or right of you, depending on which side of the theatre or the aisle you're up, you could move over a little bit if you wouldn't mind. We can make some more room for people to sit down. Tonight's speaker, Professor Stuart Wyithe, has had a long and distinguished, well actually a short and distinguished career compared to some of his more senior colleagues. I must say he has the distinction of being one of the younger professors of physics in the School of Physics at the University of Melbourne. He did his undergraduate degrees and his PhD here, but he was quickly recruited away while he was studying to both Princeton University and then Harvard University on the east coast of the United States, where he had the distinction of being a Hubble Fellow at Harvard. He returned eventually to Australia in 2004, where he quickly became a member of the permanent staff and rose rapidly through the ranks to be a full professor in 2008, 2010, a remarkably rapid rise because of his distinguished research career, which has seen him win so many numerous awards and prizes. I can only mention a few. The Pawsey Medal in 2009 from the Australian Academy of Science, the David Syme Research Prize, and finally, most recently, the Malcolm, not finally, but most recently, the Malcolm McIntosh Prize for Physical Scientists of the Year, awarded by the Prime Minister in Canberra at a gala ceremony in 2011. He is a member of the astrophysics group here at the university. He is well integrated with the international programs. He is a member of the scientific committee of the Square Kilometre Array Initiative, one of the biggest science projects of the 21st century. When he is not pondering the problem of studying the early universe, which he does using Einstein's theories, but also advanced cosmological models that run on supercomputers, he's contemplating rock climbing. Although he tells me he doesn't do very much of that these days because he's a respectable father of a young child and he's got other responsibilities, but nevertheless, like his research career, he has numerous distinctions in tackling some of the most difficult climbs here in Australia. Before I invite Stuart to the podium, can I just ask if you're carrying any device capable of receiving signals from outside, elsewhere in the cosmos, that you turn it off now. But Stuart, let me invite you to the floor.
Thank you, David, for that introduction, and thanks to everyone for coming out this evening. When I was asked to give a talk in this year's series, I was obviously very excited. And I gave the topic black holes, dark matter, and gravitational lensing, which is, arguably a little bit ambitious for 1 hour. And as became apparent once I started putting this talk together, but there are so many interesting things in cosmology and extragalactic astrophysics that have arisen from Einstein. It's very hard to choose which ones to talk about. So I'm going to give it a go tonight. All right, so I'm going to begin just with a couple minutes just to talk about, and at the very highest level, what we think of the universe looks like. So this is a really nice diagram because it shows the full range of scales in the universe, and I think we've got the wrong lighting scheme happening. Okay. All right. So this is the Earth, And if we step through these images, we see we go up to a solar system. We go from the solar system around our star, which is one star of 10 billion or so in the galaxy. The galaxy is one member of around 50 galaxies in our local group. The local group is a member of something called the local supercluster and of galaxies, which has many hundreds, thousands of such groups. And that local supercluster is part of something called the Great Wall, which is a huge structure in the universe. And this kind of structure goes on for this whole picture as far as we can see in the universe. And this is not a power of 10 diagram, it's a power of thousands or millions of diagram. There are decades of scale in between each of these pictures. And the remarkable thing is general relativity describes the interactions in space across all of these scales. That's a picture of the universe as it is now, but we know today that the universe has evolved. We know that it's been expanding, that it started with an event that we call the Big Bang around 13.7 billion years ago, and it started as it was very dense, it was very smooth, it had no structure, and over time, over those 13.7 billion years, galaxies have formed, the universe has expanded to become much larger, and it's left us with the structures that we see today. So this is the picture that we have of the universe. None of this was known in 1915, and it would be a whole and very interesting talk to try and to talk about what was known about the universe, what were physicists and astronomers' picture of the universe at the very earliest 1900s. But there was one thing that was known, so there were some distances to some of the nearby stars were known. So it was known that the solar system was not the biggest thing in the universe. But there were no distances known beyond our galaxy. In fact, the existence of other galaxies was not known. There were objects called island universes or nebula variously that turn out to be other nearby galaxies, but these were not known at the time. And so no, K-N-O-W, that's a typo. No information about the extent or the age of the universe. Okay, so all of the observations that define our understanding of the universe and that we put into general relativity to get this picture were not known. General relativity was not something that was developed in order to explain these cosmological observations. It was something that predicted what the universe would look like. So let's step through some of these important observations. This slide shows a few galaxies, and each of these galaxies has light which has been shifted to redder wavelengths. So the light from the galaxy looks redder than it was when it was emitted. So this is light. This is the same effect that you get if a light recedes from you. It's the same effect that you hear when a police siren goes past. When the car is moving away, the siren is getting lower in pitch. And this Z, larger Z, means more of this redshift. Now, if you look at these images, each galaxy at higher redshift out here, the wavelength has been shifted by a factor of 1/2. These galaxies get smaller in addition to getting redder. And it turns out that these galaxies, once they could be measured, the distances to them could be measured finally, they turned out to be also further away. And there's the famous Hubble Relation, which relates the distance to these galaxies to the velocity with which the reddening of the light tells us that they are travelling. This distance and this velocity are related through something called Hubble's constant. And this Hubble's constant is the behaviour that you would see if you have galaxies in red here in a green universe and this universe was expanding. This is what Hubble and his colleagues discovered. More distant sources lead to larger redshifts. It implies a universe that's expanding, all galaxies moving away from all other galaxies. So this is a very important observation in our universe. Now, if redshift maps to distance in a way that we can understand, it means that we can go out into the universe, observe hundreds of thousands of galaxies, and measure how fast they're receding from us and make a map. So this is one such map. This is called the 2DF Galaxy Redshift Survey. And you can think of these maps as like a pizza slice in the sky. Okay? So we're here in the middle. This is distance out away from us. And around here is an angle in the sky. And we're looking at a thin slice. Okay? And every dot on here is the position of one galaxy. And the thing that you notice about this is that these galaxies don't exist randomly in space. They have a particular structure, which we call the cosmic web. They have these little filaments and sheets which join up dense knots where there are many, many galaxies. So you can use techniques like this to get a snapshot of what the universe looks like today. Okay? It's not random. It has structure. And that structure will be very important, as I'll come back to in a moment. You can make maps like this for the whole sky. So this is a map of the whole sky of galaxies, and it's on an oval. If you think about wrapping the outside of this oval back to a point behind your head, you can be on the inside of a sphere. And so this is the way that we project the sky that we see onto the page. When you do that, you can see the galaxy, our own galaxy, moving through here, but everything else are other galaxies external to our own. And what we find when we look at an image like this is that the universe looks the same in every direction. And it also looks the same in different parts of this. If you look a long way into the distant past in that direction, a long way in the distance in the other direction, those two regions of the universe are also the same. So the universe that we observe is isotropic. It looks the same no matter which direction we look in. But it also is homogeneous. It will look the same no matter where you are in the universe, on average. Okay? Not on small scales, but if you look on large enough scales in the universe, large enough pieces of the universe, then it is homogeneous and isotropic. So that's the universe we live in today. It's expanding, it's homogeneous, and it's isotropic on large enough scales. But this finite speed of light gives astronomers a big advantage in terms of trying to study how things came to be the way they are. Because if we look at an object which is at a large distance, we're not seeing that object as it is now. We're seeing it as it was at the time the light left. So the people in the back of the room see me talking a very small fraction of a second later than David down here at the front, because the light takes that little bit of time to travel to the back. Now, this gives us a kind of cosmic archaeology. If I look I can look to very large distances, and as I look to increasingly larger distances, I'm seeing the universe as it was when it was much younger. And so by looking further and further back in space, I'm also looking further and further back in time, and I can build a history of how the universe evolved. The oldest light that you can see, the most distant light that you can see, comes from something called the cosmic microwave background. And this is light that was emitted from the whole of the universe at a time 300,000 years after the Big Bang, when the universe first became cool enough for light to travel. So it offers us it's seen over the whole sky as a kind of uniform radiation, and it gives us a glimpse of what the universe, a quite detailed glimpse of what the universe was like at that time. In particular, it tells us how matter was distributed. There were no galaxies and objects at that time, with just an almost smooth field of density, a very dense universe, almost smooth, but with some small fluctuations. And it gives us very detailed statistical information about what those looked like. So we actually have very detailed information about what the universe was like very early, and we have quite detailed information about how the universe is distributed, or matter in the universe is distributed today through maps like the one that the 2DF survey made. And what we would like is a way of understanding how the universe evolved through its history, from that very early times to what we see today. And it's general relativity that provides the framework within which we can do that. So we need to say a couple of things. You probably, if you've been coming to these talks for the last few weeks, you will have heard these very important aspects of general relativity. But there are a couple which are particularly important if you're talking about the universe as a whole. So the central proposition for general relativity is this equivalence principle. It says that essentially there's nothing special about gravity. Okay? The effects of gravity are exactly equivalent to the effects of any other acceleration. And that's not how people thought about physics prior to 1915. So what does that mean? It means that if this room, could be, which is in this blue box here, if this room were sitting on the Earth like it is, and we feel the effects, we feel a floor pushing up on us, we feel we have light travelling from the projector screen to you and so on. We have sound travelling. If this room were in space with a big rocket under it, accelerating us at 9.8 kilometres per second in some direction, we would not be able to tell which environment, there would be no way for us to tell which of those two cases were true. And this is the central difference in a way, or the starting difference between a general relativistic way of thinking about gravity and the traditional way of gravity as an attraction between two massive objects. So we do feel a force. So what is that force? Well, what Einstein said was that mass distorts the space-time in which the bodies move. So the bodies do want to go in straight lines, just like Newton had said, but the straight lines are not what we think of traditionally as straight lines. The straight lines, as viewed from someone far away, from a curved region of space, don't look straight. They look curved, but they look straight to the person who's travelling. So curved space-time requires a new definition of a straight line. It's a trajectory that's followed by an object which is experiencing weightlessness. Okay, so this is a visualization of that. If we lived in 2 dimensions, a massive object would distort this 2-dimensional space. And a ball rolling around this space doesn't feel a force. That's where it goes naturally. Okay? And a light ray through this 2-dimensional space would curve like this. Locally, it's always travelling straight. But if I'm viewing it externally, I see it as a curve. So general relativity provides us a theory to describe space, time, and motion in the presence of a massive object. Okay, so what is the universe as a whole? You can think of the universe as a large, massive system. It has mass, which creates curvature of space, and then the mass in the universe moves freely within that curved space. And Einstein's equations provide us a way of understanding how this evolution would evolve, depending on what the universe is made of. And I don't want to get into details, but the particular point is here we have density and pressure. And we're used to thinking of, if you have a dense object, we're used to thinking of that as creating gravity. If I have a dense object, other mass will want to move towards that region of where there's density because of gravity. Okay? What Einstein's theories told us is that energy and mass are equivalent. And if I have pressure in a material, pressure can only push something if there's no pressure on the outside. If I have a balloon full of gas, a particle in the middle of the balloon doesn't feel any force. It's only the edge of the balloon that feels a force. But the pressure is motions of the gas, and that's energy. And that provides additional source of gravity in Einstein's theories. And different materials, which can include light, have different relations between density and pressure. And so different materials a universe composed of different materials will evolve differently. So I just want to show one plot to illustrate this, because I think it's a remarkable observation that you can make. So we mentioned that velocity is related to distance via Hubble's constant. That's what Hubble discovered. And general relativity provides us a way of understanding how the universe will evolve, how it will move with time, given the mass that's present. And the equation looks like this in terms of Hubble's constant. Okay? So Einstein's equations tell us that we have a value for Hubble's constant now, but it would have been different in the past. If I'd lived in the universe 2 billion years ago, I would not have seen the Hubble's constant I see today. I would have seen a different value. And because light travels at a finite speed, if I look far enough back in time, I can measure what Hubble's constant was. And this has been done on a plot like this. And I can use Einstein's equations together with this data to understand what the universe was made of. And this is the kind of measurement that tells us that dark energy must also be present in the universe, in addition to dark matter and the baryons, or the normal matter that we see in the stars and planets around us. It's the kind of measurement that led to the Nobel Prize 5 years ago. Okay, so Einstein's equations give us a way of understanding how the universe has evolved with time. I mentioned that the matter curves space. Okay, so what is the shape of space in the universe? Is it the normal flat space that we tend to think of, or like the case of this apple distorting the sheet, is the space curved? And that matters to how we observe the universe, because if the light that we see from distant objects is not travelling in straight lines as we observe them, then our universe will look quite distorted. And indeed, in some parts of the universe, we do see that, as we'll come to later. But the microwave background gives us a picture across the whole sky, and it travels through the full history of the universe. So we can use the pattern in the microwave background to try and understand what the geometry of the universe is. And what I mean by geometry here is if I have a shape described by angles and lines, say, for example, a triangle is the simplest case to think about. In this room, if I draw a triangle, the angles in that triangle add up to 180 degrees. If I have a universe which is closed, then those angles would not add up to 180 degrees. They would add up to more than 180 degrees. And you can check that if you have a ball at home and you draw 3 straight lines on the surface, you'll find that the angles are larger. And similarly, in an open, something called an open space-time, they would be less. But when we observe the microwave background, we see a pattern which shows us a universe which is Euclidean. It's flat like we're used to. And that posed a very large problem for cosmology, which was solved by inflationary theories a few decades ago now. Okay, so Einstein's equations provide us with a means to understand how the universe expands. They provide us with a means to understand the shape of the space-time that the universe is evolving in. They provide us a means to understand how massive bodies will interact gravitationally with each other. And so we can take all of this information, cosmic microwave background telling us what the universe was like at the very earliest times. And we have a map of where the matter is distributed in the universe today by looking at where all of the galaxies are. And we can make a supercomputer model to take this matter and evolve it to the present day to see whether our theory is correct, to see if we can understand how this pattern of structure came to look the way it does. And this box is not expanding. The expansion has been taken out to make the plotting easier, but in the simulation, the space also expands. So what you're seeing here is perhaps around 1 billion particles in the simulation evolved across the history of the universe, and the size of this box is a few 100,000 light years on a side. So all of these little specks here are galaxies-sized objects that form in the simulation. And you can see the patterns qualitatively are the same. Now, if we change the material that the universe is made from, more dark matter, less dark matter, more dark energy, less dark energy, and so on, we get different patterns in that galaxy distribution that we predict. And this gives us another way of trying to measure what fraction of mass is in the universe. So we have multiple handles on this, and all of the different ways of measuring the amount of quantities of dark energy and dark matter tend to agree. And they come up to this, this pie chart here, which is known as the Concordance Cosmology, or the lambda cold dark matter cosmology. 70% of dark energy, 25% or so of dark matter, and around 5% of ordinary matter, the matter that makes up our solar system, our planet, the sun, a very small fraction. And so, but these numbers are known now to some high precision. And so you're tempted to think, well, is cosmology done? How could we all go home? And of course we can't, because for lots of reasons, but not the least of which that we have no idea really what dark energy is or dark matter. These are fields of ongoing research to try and understand what these materials are, where do they come from, which aspect of our theories for particle physics are missing the key piece of information. So I want to talk about dark matter. I'm not going to talk about dark energy today, but I do want to talk about dark matter a little bit, because it's the dominant contribution to our galaxies in terms of how they form. So for the purposes of trying to understand galaxies, dark matter is something which has mass but does not interact except through gravity. So if I have a large volume in which I have a dense region of dark matter, and that dark matter will distort the space-time around it, and it will affect the motion of other bodies. But if I shine a light on that dark matter, the light will go straight through. There's no interaction with the light. Okay. So and hence the name dark matter. Okay, so we can't see the dark matter, but we can infer its existence by looking at what it does gravitationally to other bodies. So this is a nice acute animation, in fact, of the solar system. Okay, so here showing planets orbiting the sun and moons orbiting planets. But the solar system is not the only place where bodies orbit. If we look at a galaxy, a star in the galaxy, all of the stars are orbiting this galaxy. They're not orbiting at a rate where we see them go round in real time, but if we look at how the light from stars in other galaxies, our own galaxy, we see a shift which tells us that those stars are moving, and we can measure how fast they're going. Similarly, if we go to a cluster of galaxies, so each of these red images here are galaxies in a big cluster of galaxies, some thousands there. Those galaxies are not stationary; they're moving with some velocity, and they're orbiting the mass which is made up by all the other galaxies. So it's gravitation that's keeping these systems of stars and systems of galaxies together. And so we can use, in the same way as we can use the speed at which planets orbit the sun to measure how massive the sun is, we can use the speed at which stars orbit the galaxy and in which galaxies orbit the cluster to measure the mass of those very massive systems. So if we look at a galaxy, this is a graph which shows the radius of the galaxy, and it's in thousands of light years. And on this axis is the velocity in kilometers per second. And superimposed on this is a picture of a galaxy to give you an idea of the scale relative to a galaxy you're used to looking at. So if I look at this mass and I add up, I know if I look at a star, it's a bit like the sun, I know how heavy it is. I can add up all of this mass. And I can use an equation, in this case, an equation that I would get from Newtonian gravity, but in the limit of very low densities, like we have in galaxies, general relativity gives me the same equation. I see a curve which looks like this. Okay? So I would see velocities circling this galaxy which go up while I have all this more and more matter enclosed. But once I get to a certain point, I run out of matter, and so my velocity will start to go down, just like it does in the solar system. As I move to larger and larger distances from the sun, the rate at which the planets move drops. But that's not what you see. When you make this measurement, you see velocities which keep getting larger and larger and larger, all the way out to extremely large radii, as far as you can measure. far beyond where you see any more stars or any gas. And the implication, which was realized in the 70s, is that it's dark matter that's existing here, and we see it through its effect gravitationally, but we have no other way of determining its presence. So if we could see a galaxy moving in real time, they would look like this. So if a galaxy had no dark matter in it, just the matter we could see, we'd see fast moving stars in the middle, but on the outside, slow moving stars. And this is what you see in the solar system, much slower movements far away from the sun. But what we see in a real galaxy is that the movements out here far away from the center are just as fast as the ones in the middle. There's some more matter there that we can't see, 10 times as much mass that we can't see. So what about clusters of galaxies? Clusters contain thousands of galaxies. So we could add up all the mass from all of these galaxies and calculate how heavy this cluster would be. And we get a mass, some tens of thousands or more times the mass of a single galaxy. But galaxies, like all other objects and clusters of galaxies, can be observed not just in the optical light that we're used to thinking about for astronomical objects, like the pictures I've been showing, but you can look in all sorts of different wavelengths, from radio all the way through to gamma rays. For example, X-rays, and objects look very different depending on how you look at them. We also know that if you heat gas, light comes away. Okay? So in fact, the sun, when you're looking at the sun, you're looking at radiation coming from very hot gas. Okay? And that gas is, thousands of degrees. It's the sort of temperatures that we can see with our eyes. But if you make really hot gas, like 1,000,000 degrees, then that gas emits X-rays. And the gas, that's what you see when you look at a cluster in X-rays. You see large amounts of really hot gas, a million degrees or so, and it's covering the extent. You see the little galaxies in red, all this blue area. This is emission that you get when in X-rays. X-rays are coming from all of that region. Now, gas, if hot gas, in the lab you can heat gas up and measure how much radiation comes from that gas. So you know that if you see a certain power in X-rays, you know how much gas was present. So you can add up all of the hot gas that you see in these clusters of galaxies, and you find 10 times as much mass in that hot gas as you see in the galaxies themselves. So if you look at a cluster of galaxies, even the normal matter that we're used to thinking about, the material that the Earth and solar system are made of, there's 10 times more of that material evenly spread through the cluster of galaxies than there is in the galaxies themselves. But now we can play the game where we measure the motions, how fast these galaxies are moving, and try and measure the mass by looking at the velocity as a function of how far away the galaxy is. And when you do that, you find that there's another 10 times as much mass present in the cluster of galaxies than there is in the X-rays, than there is in the hot gas from X-rays. Only 1% of the mass in a cluster of galaxies is made of stars, and the vast majority of it is, again, an unseen dark matter. Now, so far, all the ways that I've mentioned of finding the dark matter are to do with the motions of mass in the presence of a curved space-time. Okay? But there is another way, and that is to look at something called gravitational lensing. I mentioned right at the start that if you have a mass which is distorting space-time, radiation travelling through that space-time will appear to be curved, will appear to travel on a curved trajectory if you look at it from far enough away. Okay? So the photon, this is showing this figure again. Here's my curved space-time. My photon would travel along one of these straight lines far away from this mass, but near it, there's locally curved space-time. And so if I'm standing here, this photon appears to bend. Okay. So what does that mean if I look in the universe? Well, this is This is an example of a gravitational lens. You can do this yourself when you go home. It turns out that mathematically, the way in which an object looks when you view it through a distorted space-time by a massive object has mathematically the same properties as an image viewed through the conical shape of the bottom of a glass stem. And so what you see is your image ends up with these arcs and rings, and you get multiple images of the same bit of the picture. And you see this in the universe. Okay? So in the universe, if I'm looking with my telescope towards a very distant galaxy, if there's a foreground galaxy in front at about half the distance, that galaxy will distort the space-time around it. And so the light from this galaxy behind will not have a flat Euclidean universe to travel through. It will be traveling through a bit of universe which is not Euclidean, which has curvature because this mass is in the way. So these photons will travel around the corner. It could go both ways. It could go on more paths than that. And I instead see two images. I don't see the original galaxy. So this is the observer's view in this schematic situation. These are some real pictures from the Hubble Space Telescope. You see some examples where the red is the galaxy in front, and you see 4 images of the one behind. Here you see 2. Sometimes you see an arc like this, which is what you could see through the wine glass. They're not really common, but they're not rare either. You see there are many, many hundreds of these known. This looks more like the wine glass. This is what you would see if a cluster of galaxies, which is the red galaxies, moving across the sky, and the blue galaxies are the galaxies that are behind. You see these arcs that form at different times. And this looks beautiful in simulation, but it looks even better for real. This is a picture of a galaxy cluster. You see the red galaxies here. And if you look in this picture, it's probably not quite dark enough in this room, but you see many arcs. Okay? They're in circles that come around here. And indeed, any time you look at a big cluster of galaxies, you look deeply enough with a telescope like Hubble Space Telescope, you see these arcs. It's a uniform phenomenon. It happens in every cluster. Okay, so general relativity we can use to calculate how the mass bends the space-time and what that does to the trajectory of the light. And so by making measurements of these arcs behind the galaxy clusters, we can measure how massive that galaxy cluster is, because the bigger the cluster, the more arcs I'll see, the more spread out they'll be. And we find that the measured mass agrees with what we get when we look at the orbits of the galaxies. The theory is consistent whether it's talking about the bending of light or whether it's talking about how galaxies move in the gravitational field. So it's not just the orbits it's not just evidence from orbits of bodies, it's also gravitational lensing. But if you were a skeptic, you could say, well, what if general relativity is wrong? The only measurements that we've made which we can, in a lab are on much smaller scales, where here we're making cosmological measurements, they're far away. We can't do an experiment on the universe. Okay? Perhaps we've just got gravity wrong. But there's fabulous objects called bullet clusters which provide a test of this. Now, if you look at a galaxy cluster, you can look at where all the galaxies are, and you can look at where the hot gas is, the X-rays, tell you where that hot gas is. Now, if general relativity is wrong, that might be all the matter that was there, no dark matter. But if you look at a bullet cluster, these are where you have 2 clusters nearby, and you can see 2 separate clusters, one with the orange galaxies here and one here. And what's shown in the red here is the very hot gas that's emitting X-rays. Now, if I do a gravitational lensing experiment on these clusters, I find that this is where all the mass is. Okay? It's lined up with the galaxies. It's not lined up with the gas, which is here. Now, we know that there is 10 times as much mass in the gas that's emitting X-rays as there is in the galaxies. And that's physics that we do understand. It's experiments that we can do in the lab. But when we do the gravitational lensing, we find the mass is out here with the galaxies. So it's not our gravitational theory that's wrong here. It really is, what's happening is the dark matter, in fact I've got a movie to show this. What's happening here is that two clusters of galaxies which contain gas, stars and dark matter crashing into each other. Galaxies have lots of stars in them, but they're very empty. And so when they collide, the stars just pass through each other and they interact only gravitationally. The dark matter does the same thing. But the gas has pressure in the sense that we're used to. If you collide two gas clouds together, they will slow down. And so as they pass through each other, the gas slows down, but the stars and the dark matter keep going, and you're left with this material in the middle. So this is really difficult to refute evidence for the existence of dark matter. It's not something that's wrong with general relativity. Okay, so I want to segue now into black holes, and I will bring the black holes and the galaxy formation back together in a moment. But general relativity is explaining how the universe works on the very largest scales for clusters of galaxies, how clusters of galaxies are distributed across cosmic time, the very biggest scales that we can study. On the very smallest scales, we know that mass is being well, not the very small, on smaller scales, the mass is being distorted, the space-time is being distorted by mass. So if I have a massive body like a star, it distorts the space-time nearby. And we've said that bodies in orbit are freely falling through this curved space, and photons that are traveling will bend if you view them from far enough away. Okay, now what if I take this object and I make it denser, more mass, put more mass in this central region? This will distort the space-time more. Okay. So let's think about that from our normal experience. If I'm standing on the surface of the Earth and I throw a ball at 10 kilometers per second up, that's pretty fast, but that ball will come back. It will take a while, but it will come back down. A ball thrown at 11 kilometers per second will not come back. That's what's called the escape velocity. Now if I can calculate, this is a calculation I can do with Newtonian physics. Okay? If I do the same calculation for an Earth that's 100 times smaller in radius, I need to throw the ball 10 times faster in order to make it escape, because the mass that's more concentrated now, the mass of the Earth is the same, but the radius has become much smaller. So I have to do more work to get this ball to escape. If I shrink the Earth down to 1/3 of an inch, maintaining its mass, then I have to throw the ball at 300,000 kilometers per second, and that's the speed of light. So now Einstein's theories tell us that nothing can go faster than the speed of light, and this is experimentally what we find also. So this object, if I have an object like this, if I'm on the surface, it's not possible to communicate with the outside world. Okay? Light is unable to escape. For the sun, if I shrink the sun down to 3 kilometers, I have the same phenomenon. Okay, so how do I understand this in general relativity? If I look again to my rubber sheet analogy, my two-dimensional analogy, and I put my mass in the middle, and I make it bigger and bigger, then what I do is stretch down this central funnel. So now imagine looking at this surface from the top. I see a body traveling in towards the center. When it gets to the edge of this funnel, it will travel down here. But viewed from the top, it'll be stationary. And so general relativity defines a black hole to form at the point where the rate of change of this position is observed to go to 0. So if I look at a black hole in the universe, and if I could watch something traveling into the black hole, I would see it stop at this radius, which we call the event horizon. And anything within that radius can't be observed. So black holes are a prediction from general relativity, and a lot of time and effort was spent over the past 100 years trying to discover them. One path is that they're thought to form from the deaths of very massive stars, which can no longer, they're so massive, they have no power left, they can't support their own weight anymore, and so they collapse to form an object which is denser than this event horizon size. Okay? And those are the types of objects that were discovered by the amazing LIGO experiment recently, and those of you who heard Andrew Malatos's talk will have heard a lot about that very exciting discovery. Now, black holes, those gravitational waves represent really the first very direct evidence for black holes, really represent the discovery of black holes. But there are other black holes known in the universe, and the most spectacular example, I think, is the one that's in the middle of our own galaxy. So this is, if you look, this is a picture taken in infrared light of the center of the galaxy. And I've shown this graphic again of the orbits of planets around the sun. If you look at this picture, which is a small region in the very center, okay, this is about the size of the solar system here. You see stars. This is time-lapse over 20 years of the positions of stars observed in this region. Okay. So at this position here, we see orbits of stars going around this position where the star is, but there's nothing there. And so if you zoom in on that region and look at how fast, well, you look at as a function of radius from that central position, you can use your laws of orbit, the orbital laws, to calculate how much mass should be in a radius smaller than that position, and you find this. So if you go to a size bigger than about 1 parsec, so this is about 3 light years, you find that you get more and more mass. But below that, you find a constant value of mass. And that's just like in the solar system. If you go from Jupiter into the sun, the amount of mass within that radius is essentially the same. All of the orbital motion is caused by the sun. And here, what we're finding is that something in the very center here of mass 4 million solar masses, so 4 million times the mass of the sun, in a region smaller than the solar system, is causing these orbital motions. And that can only be a supermassive, what we call a supermassive black hole. If you look in another galaxy, this is a much bigger galaxy than the Milky Way nearby. In the center of this galaxy, M87, you see as you go into very small radii, the velocity rises. It rises the same way as it does in the solar system, and it provides evidence for an object that must be a black hole of around 7 billion solar masses, so 1,000 times bigger than the one in our galaxy. And in fact, if you look at any massive galaxy where you can do an experiment like this, any very massive galaxy, you find evidence for one of these black holes. And not only that, but these black holes have masses that seem to be related to the mass of the galaxy in which they live. They have about 1,000th of the mass of the galaxy. So these supermassive black holes have some connection with the way in which galaxies form, which is very important and which we don't yet understand. Okay, so let's come back to the evolution of structure in the universe. We've said that general relativity gives us a way to go from very early times, how the mass in the universe was distributed, to this distribution of galaxies in the cosmic web that we observe today. Now, if you look closely at this, what you see is that isolated systems form and then they merge together to form these string-like structures. So if you zoom in on a little bit, a simulation like this is zooming in on one of those knots. Each of these little regions in this simulation is a galaxy. And what you should see is that as this progresses, these galaxies merge together. They have this very messy thing, but then you have situations where two systems merge together to form one bigger one. And this is happening through the whole history of the formation of galaxies in the universe. So if every one of these galaxies houses a supermassive black hole in the center, then the mergers of these galactic systems through cosmic time will bring two supermassive black holes together. And if you bring two massive systems together, they'll form a binary system. So binary black holes produce gravitational waves. Two stellar mass binary black holes will produce the gravitational waves that can be detected by LIGO. Two much more massive supermassive black holes will produce gravitational waves at a much lower frequency, longer wavelength. So why does this happen? If one massive body, one black hole, distorts space-time in the vicinity, then if I have another one nearby and I rotate them, you can think of this as like stirring space-time. Okay? If you only have one spinning sphere, then you don't stir space-time. But if you have two, you will stir it, and you'll send out these rippling waves. And these are waves of increasing and shrinking distance in space-time. So if I have two pendula, these pendula will oscillate a little bit as this ripple in space-time moves past. So this is what was detected by LIGO. So LIGO had pendula separated by 4 kilometres and was able to detect, astonishingly, a separation change 1,000th the size of a proton. This is an engineering feat to be truly marvelled at, and I hope that many of you are here to hear Andrew speak about this. But LIGO was built to detect gravitational waves from stars. And stellar black holes were the most promising target. You can build an experiment of 4 kilometres in size to detect those gravitational waves, which have a frequency of about 100 hertz. Okay. But supermassive black holes with 1 million times more mass have frequencies which are about 1 million times lower than the frequency of the gravitational waves that are measured by LIGO. And so there is proposal and prototype missions to build something called ELISA, which is the same idea as LIGO, an interferometer shooting lasers back and forth to measure the separation or the time travel time or the light travel time between mirrors on pendula. But instead of being separated by 4 kilometres, they're separated by about 5 million kilometres, because that's the scale that you need for to measure those gravitational waves. And this is an experiment which is believed to be possible as well, amazingly. But this is the frequency of black holes with about 1 million solar masses at the end of as they come together. But for most of their lives, if I'm bringing galaxies together, they're black holes, the supermassive black holes in the middle, the really big ones, the 10 to the 10, 100 million solar mass ones, the 1 billion solar mass black holes. Those spend many millions of years orbiting one another, and they emit radiation not at 100th of a hertz, but at 10 to the minus 9 hertz. Okay, so once per 10-year kind of frequencies, extremely low frequencies, and it's not possible to build an interferometer. You're talking about a system, an interferometer that's larger than the solar system. So not even astronomers or particle physicists think that that's a good idea. But fortunately, we have another option. And the universe is full of extremely accurate clocks, known as neutron stars, or pulsars in particular, which are neutron stars that are rotating. So a neutron star is a star that was not massive enough to become a black hole. The neutrons that were left had sufficient stiffness to hold the star up against gravity. But they're very small. They weigh up to 2 solar masses, but they're about as big as Melbourne. And you can imagine if you're spinning something as massive as the sun but as small as Melbourne at 100 or 1,000 times per second, it's a pretty good clock. Not much is going to move that. And so the radio waves that come out of the pole of this star and sweep across the Earth, give us a very regular clock. And in fact, though the team, particularly at the Parkes Radio Telescope, Matthew Bales has been the leader of this, who was giving a talk here last week. They've managed to time the arrival of from these pulsars at a nanosecond over some decades. Incredible precision. So using the pulsars, you can measure the time of arrival of pulsars over a period of decades, and see if the time of arrival changes. And that time of arrival change from pulses from these pulsars tells you that the space-time has changed in between our position and the pulsar's position. And you can use this effect to look for gravitational waves. So here's the Parkes Radio Telescope. The pulsars are twinkling through this gravitational wave field. So this is it's similar physically to what the LIGO detector is doing, but it's doing it for a very different population of objects. Billion solar, the biggest black holes in the universe, with frequencies that are 10 to the 12 times lower. So this is the last graph I want to show you. These are the measurements. This is what's shown here is how many, you can think of it as how many gravitational, what's the size of the gravitational waves detectable from this object, from these supermassive black holes. And these are not detections, these are how well the experiment can do. And so what you see is these limits coming down to these values here. The theories are shown in blue, and they've come together. And it's a very interesting time if you're trying to understand supermassive black holes in the universe, because our best theories from how galaxies form and how black holes interact with them predict that there should be more gravitational waves in the universe than our experiments have shown exist. But we do know gravitational waves exist themselves because LIGO has found those. So there's something wrong with our theory of galaxy formation and our theory of how black holes fit in to that theory. And now we have a new handle on really trying to understand what that is. So I will finish there. General relativity has had a range of profound implications for cosmology, I think. And I've tried to share a couple of those. It's provided a framework to understand observations that go from the expansion of the universe. It's predicted black holes and gravitational lensing, and then it's helped us interpret the discovery of black holes and gravitational lensing, and also gravitational waves. If we have a homogeneous isotropic universe, the solutions to Einstein's equations allow us to weigh the universe. They allow us to understand how old it was. Measure it, understand its composition by looking at its expansion history. So this is work that's been carried out over the past decade, theoretically, in particular in the past 50 years observationally. And it's yielded a detailed model that gives us the existence of dark matter, the existence of black holes, the existence of dark energy. And it provides us with a lot of work to do in the next century to try and figure out what these are. So I'll finish there. Thanks. Thank you very much.
Well, Stuart, thank you very much for that tremendous overview. That's a very good point that you end on. We've known about general relativity for 100 years, but if you come back on the 400th anniversary of the discovery of general relativity, like we had the 400th anniversary of the telescope, who knows what we'll be talking about then, or whether it'll be even us.
Yep.
But, ladies and gentlemen, I think we've got time to take a couple of quick questions. Yes, gentlemen, right at the very front.
Thank you, Professor David. Thank you, sir. Very beautiful. How I think why we don't know dark matter, dark energy, how I think like that, not powerful technology, not too much knowledge, not powerful economy, and little bit time. That's right or no? Thank you.
So what is the main contributor to us not knowing?
Yes, knowledge, time, economy, or the technology.
I don't think it's economy. I don't think it's technology. It's probably time. I think we've only known dark energy. We've known about the accelerating universe for probably 20 years. When I was a PhD student, no one believed that the acceleration of the universe was real, only 20 years ago. So now it's an accepted fact that the universe is accelerating, but the cause of it is under debate. So that's not 20 years is, it's a long time, but it's not a very long time in terms of trying to construct a new theory for something that was completely unknown before.
Okay, was there a question up the back that I see against the glare of the light there? Yes, over here, sir, please.
I was just wondering about, with the dark matter, are you able to infer sort of velocities of the particles of the dark matter and another
Yeah, no. Yeah, so the question was whether you're able to determine the velocities of the dark matter. So I assume you mean, so like in a gas, the particles have motions, and you want, yeah. So there's two answers to that. So there's a regime when, if you look at the dark matter that's uniformly spread through the universe between the galaxies, that dark matter is called cold dark matter, or warm dark matter, depending on the flavor. And what's meant by cold dark matter is that the motions, the internal motions are very small. And you can measure how small they must be by looking at whether small structures can grow. So basically, if you have very fast motions for the dark matter, you start off with a little fluctuation in density which could grow into a galaxy. But before it has time to grow into a galaxy, all the particles moved away because they were traveling too fast. So dark matter is very cold in the sense that it doesn't move very fast, because if it did, we wouldn't have the little galaxies. So that's the one type of motion. The other type of motion is after you form a galaxy, the material has come from sort of near uniform density in the universe and it's fallen in. And as it's fallen in, it's gained kinetic energy. And what happens to the gas, like the hydrogen, is that it gets very hot when that happens. And it radiates away. But the dark matter has no way of radiating the energy away, so it just keeps moving very fast. So if you look in the cluster of galaxies, the dark matter is moving at velocities that correspond to 1,000,000 degrees if it were a hydrogen gas. But it has no way of shining. The particles just move. And that's why they don't collapse into a dense region, because they have these motions.
Okay, ladies and gentlemen, I'm going to wrap up the proceedings now. So, Stuart, thanks again for a wonderful and very broad-ranging lecture. Ladies and gentlemen, thank you very much for coming. Please stay tuned to the various websites. We will have another program of July lectures next year, and I look forward to welcoming you all back again. Thank you again for coming, and thank you, Stuart.
Thank you.